Hello again. In this part of the lecture, we are going to discuss the second type of synchronous generators called the wound field synchronous generators. We're going to understand their construction and develop their equivalent circuit in a similar manner that we have done for the motors. And we are going to work on an example to solve a related problem. The wound field synchronous generator is similar to the permanent magnet generator, but with the permanent magnets replaced by electromagnets on the rotor. So you can see here inside, this is the rotor. It has some windings, and when DC current is supplied to these windings, they produce a rotor magnetic flux, which is then induced in the stator, and that produces the phase voltage or a three-phase electrical output. This shows a simplistic two-pole rotor winding, but in reality, high pole numbers are common. It is also important to know that large synchronous generators are fixed speed machines to give a fixed frequency of 50 Hertz as an output voltage. So if we look over here at the construction of the wound field synchronous generator, we can see that the rotor is connected to a prime mover such as a wind turbine, a water turbine, a gas turbine, and there is a DC supply which is connected to the winding of the rotor. So as the rotor is moving, the DC current that is flowing inside this winding will produce a magnetic flux, and this magnetic flux is going to strike or cut the stator winding, and this would cause a three-phase voltage output in the stator, of course, if the stator windings are connected in a three-phase shape. And the prime mover rotates the shaft at a given speed, and the DC current, which is identified as IF in the field winding, produces the rotating magnetic flux. And as the flux links with the three-phase rotator winding, this produces the three-phase sinusoidal voltages from the three stator windings. And these windings, then, they are connected to any electrical load. It is also good to know that the windings of the stator could be either delta or Y connected, but the most common one is the Y connected three-phase stator windings. Let us take a look now at some differences between the PM generator and the wound field generator. Let's consider first the rotor flux. So in the case of a PM generator, this is fixed. But in the case of the wound field generator, this is defined by the DC current. The excitation voltage is set by the speed of the rotor. However, in the wound field generator, it is set by both the speed and the current, which is typically, and the speed in this case is typically fixed. The voltage frequency, so the frequency of the electrical voltage output. This is set by the speed of the rotor in the PM generator, while in the case of a wound field generator, this is set by the speed, which is typically a fixed speed. In the next slides, we are going to discuss the operation of a wound field generator. So let's see in more details what is going on. So the rotor is fed by a DC current. As the rotor rotates, this will cause the rotor field intensity to change, and therefore the rotor flux changes accordingly over time. And the change of the flux over time produces the three-phase stator voltage, which is called as the voltage of the phase. So we can control or regulate the stator excitation voltage by controlling the DC field current. So you can see this is a major factor for controlling the output voltage of this type of generators. And we can see that as the field current increases, the stator voltage increases linearly up to a specific point. After this point, what would happen is the saturation of the iron laminations at high flux levels. And that's why we see the curve over here. So it's always desirable not to reach to this stage. So that's why the field current is limited before this point. Let us now take a look at a Y-connected stator winding. So in this case, there are three-phase voltage, and the line currents are called IR, IY, and IB. Notice that the DC field winding current creates the rotor magnetic field and induces three proportional AC excitation voltages, ERN, EBN, and EYN. And notice that in each phase, there are the stator winding resistance, which causes some losses, as well as the leakage inductance. Now, if we take a closer look, so if we zoom in and take only one phase equivalent circuit, we will see that it looks something like that. This is very simple. So over here, this is the excitation voltage, which is set by the current IF. And this is the stator winding resistance, which is usually negligible because the drop across it is ignored. And over here is the synchronous reactance. This is the terminal phase voltage or the output voltage. So if we remove the resistance, we will have a very simple circuit which looks something like that. And if the phase voltage is connected to a load, we can see that the phase current will flow through the inductance reactance as well as the load. And the magnitude and the phase of this current is determined by the excitation voltage, by XS, and by the load. And the terminal voltage can be determined once we know the phase current. So notice that the magnitude and the direction of the phase current is equal to the phasor sum of the phase voltage, which is dropped across the load, and the voltage that is dropped across the induction reactance. If we look further into the phasor diagram of this per phase circuit, we will see that if we put the phase voltage on the reference axis, its summation with the voltage across the induction reactance gives us the excitation voltage. And between them an angle, this angle is called the load angle. However, if we look at the current flowing in the circuit, which we call the phase current, we will see that the difference between it and the phase voltage is phi, or theta sometimes called, and this is the famous power factor angle, which is the angle between the phase voltage and the phase current. Notice that the voltage across the synchronous reactance leads the phase current by 90 degrees, and that this is the phasor arithmetic in order to calculate the excitation voltage. All right, so let us see how this phasor diagram is connected to the phasor diagram of the real power, the reactive power, and the apparent power. So let us assume that we have multiplied every component, every voltage component that you see here, by 3 times the magnitude of the phase voltage divided by XS. Notice that this would lead to this diagram. And if we extend this further, we will have over here the reactive power. Notice that this is theta or phi as indicated previously, and hence geometrically speaking this would be also theta, and that will be also theta. And if we extend that triangle outside over here, we will see that this produces the reactive power, and over here we have the real power, while over here this gives us the apparent power. Now let us play around with some variables. So we can see that sine the load angle can be given by this formula. And if we rearrange the formula, we will get it in terms of the real power. So in order to change the output real power, one of these can be changed. but it is always desirable to keep the load angle below over here to avoid stability problems, because when the load angle becomes 90, then the power becomes very high and there will be some problems in the lines of the magnetic flux. So basically what would happen is, as the load angle reaches up to 90 degrees, half a pole of the magnetic poles pitch and the stretched flux lines get broken, and hence the magnetic locking between the stator and the rotor no longer exists, so the motor comes out of synchronism. So that's why we keep a safety margin, and the load angle is chosen to be somewhere in this region. All right, now let us put what we have learned so far into a practical example. I would like you to read the example and spend about 10 to 15 minutes solving it. In the next video, we will solve it together.